So let's now talk about the frequency domain representation. So we have assumed x of t to be a signal which contains the frequencies from 0 to fm. So fm is the maximum frequency that signal x of t contains. So this first spectrum that we have drawn is the frequency spectrum of signal x of t. I will call it capital X of f. Frequency domain representation is always with respect to f. How do you find the frequency domain representation? For that, all you have to do is take the Fourier transform of the signal. So if you take the Fourier transform x of t, we'll understand what are the various frequencies present in the signal, and we have plotted those frequencies in this x of f. To be precise, we have plotted the magnitude spectrum of the Fourier transform of x of t. We are not much interested in the shape of the spectrum. You can see we have assumed it to be a simple triangular shape. It can be any other shape in practice. All we need to remember and consider is that there are frequencies from 0 to fm. Because Fourier transform gives us two-sided representation, I have shown the spectrum going from minus fm to plus fm. But please remember that practically we always talk about the positive frequencies. So the frequencies present in x of t are from 0 to fm. So if I want to write bandwidth of this signal, the bandwidth of signal x of t that we have taken is equal to fm. Please remember that bandwidth is always found from any one side. All the real signals will have E1 magnitude spectrum, and hence whichever side you consider, the bandwidth, the width from the minimum frequency to the maximum frequency will be exactly same. In this case, it is fm. So fm is the maximum frequency in the signal, and hence it also becomes the bandwidth of signal x of t. The next thing we want to do is write down the frequency spectrum of the sampling signal s of t. S of t was a time domain signal. Now we get s of f, which is a frequency domain signal. If you observe carefully, we have shown three impulses in the frequency domain representation. But these are not just three impulses. As you can see, I've put the dots. That means there are multiple impulses all occurring at a specific gap. In simple words, the Fourier transform, the frequency domain representation of a train of impulses is also a train of impulses, because if you observe carefully, this second signal which we have shown, which is nothing but the Fourier transform of the second time domain waveform, is nothing but a train of impulses. So the train of impulses on the frequency domain side, as you can easily make out, is a function of frequency f, because it's a Fourier transform now. There is one impulse at 0. You can see the second impulse occurs at fs minus fs. If you want to show fourth and fifth impulses, they will occur at 2fs, minus 2fs, 3fs, minus 3fs, and so on. Otherwise, the Fourier transform of train of impulses is a train of impulses. But what is the difference between the two? The difference is the gap between the impulses. You can see the gap between the impulses when the signal is in time domain is Ts. The same gap between the two impulses when the signal is represented in frequency domain is Fs. And what will be the relationship between Fs and Ts? The relationship says that Fs will be equal to 1 upon Ts. So if the Ts was sampling period, then let me mention that Fs is nothing but sampling frequency. If Ts is 1 microsecond, Fs will be 1 upon 1 microsecond, it will be 1 megahertz. That means 10 raised to 6 hertz, and that will simply mean that in 1 second, I will be reading 10 raised to 6 samples from x of t. I repeat, if Ts is 1 microsecond, that means after every 1 microsecond, we will read 1 sample from x of t. So in 1 second, how many samples we will read? So in 1 second, we will read total 1 upon 1 microsecond number of samples, which will come out to be 10 raised to 6 samples. So please remember that sampling frequency always tells you how many samples you are reading from the signal per second. If the sampling frequency value is, let's say, 1 kilohertz, that means you are reading only 1000 samples per second. If the sampling frequency value is 10 kilohertz, that means you are reading 10,000 samples per second and so on. If the gap between the two impulses in time domain is less, that means if the value of Ts is less, then the gap between the two impulses in the frequency domain will be more. In other words, Fs will be more. So if Ts is small, we had concluded that the loss of information is less, and that means the loss of information is less also corresponds to the greater sampling frequency.